Okay, I'm sorry, but I have to cut off your vivid discussions about the project. That's at least that's what I assume. What you're talking about. Do you have any questions, sort of, for this big ground? Anything in terms of logistics? Of course, smaller, more detailed questions we can always do in our office hours, but nothing big. Then I would immediately go into our topic for today, which is going to be fun. The lesson that we learned today is, well, today and Thursday, is that stuff that looks nice isn't necessarily nice. And this is just something to, I think, to keep in mind as a general life lecture if you become an engineer. And what we did last time, we talked about computational complexity, which is the question of how computation time or computational effort scales with problem size. And I gave you the formal definition of this order n notation, where a function g of n is of order f of n if it fulfills sort of these rules, which basically mean that it scales less or equal than f of n. There is, for everything that we will do in this class, there's a different, more practical way of looking at computational complexity. And today I will skip through my notes a little bit because I want to actually start with an example to give you this second view onto computational complexity. And what I have here is two MATLAB implementations of, on the left-hand side, we see a dot product. And on the right-hand side is not a dot product. This is row vector times column times row. So this will give us a matrix. And if I look at this, right, the way you would implement this naively is through some for loops, where, say, if I compute a dot product, I initialize a result to be 0, and then for each element in these two vectors, I add the product of these two elements to my result, and this is going to give me my overall dot product. And this means I have here a single for loop which runs from 1 to n, and everything that happens within this for loop is executed n times. And this basically means this is something that scales linearly in time. If I double n, my for loop runs twice as long, and I have twice as many operations, roughly, right? Just scaling, because this is not exact. If I count the total number of operations, of course I have to initialize, and I have to initialize the for loop, and there's things that I only do once, but there's this big chunk here that I do n times, and of course if I double n, then I have to do this twice, or twice as many times, and this is what dominates my scaling. If I look at this other product here, x times y transposed, we know that the result is a matrix. And I now have to initialize here not a scalar value, but this is a n by n matrix, right? This is MATLAB code for n by n square matrix of zeros. And to compute the elements of this matrix, I now have to have two nested for loops. So I have my column index, my row index and my column index. And with this, I can basically directly compute the element ij, column row, the other way around, row column, which is the product now of these two individual elements. And the key thing here, the key observation, is that we have two nested for loops, which both run from 1 to n. But if I double n, then I have twice as many operations in the inner loop, and I have twice as many outer operations. So I have a total of 4 times as many calculations. And so if you read somewhere order n square, think of 2 nested for loops. If you read order n3, there's somewhere 3 nested for loops, and so on. And with that in mind, I jump back to my first page of the template, and now I can give you some examples, right? So capital O of n, right? And we would read this as order n. Some algorithm is order n, which means the problem scales linearly. And the examples that we looked at were, or we just saw, a good example is a dot product, right? Where you have to go through all indices from these vectors at once, add it all up. So you have n multiplications, n minus 1 additions, depending on how you implement it, total something times n operations. And then I can do order n square, right? And this stays all the same. Now the problem scales quadratically. You have an example for a quadratic problem. We just saw row times column, right? You have another example for something that would scale there's half of the words missing, right? Quadratically, half of the letters missing, sorry. Who can think of another operation where we have two nested for loops?
There's something we took back in the days where you have to make like a star-shaped, I think, shapes in the code to add nested for loops also. It's like trivial, like doing shapes with stars and stuff.
We did this?
No.
Oh, okay. Okay, then that's why I don't remember this example. Any other ideas? This here, right? If I have here a n by n matrix, and I multiply this with an n-dimensional vector, where are the two for loops? Well, matrix times vector is basically n dot products, right? Every row has to be multiplied with the vector, as in the sense of a dot product. So I'm basically doing here n individual dot products, and that means I'm doing n times n operations, n square operations, or the way you would set this up is through two nested for loops. Right? And in practice, whenever there's a matrix involved, it has to be at least order n square. Because just putting that matrix in memory or just writing the matrix down is an order n square operation. Because a matrix will have n square entries. Cubic. You have an example here for something where you need three nested for loops.
A vector pre-multiplied and Boston multiplied by a matrix.
Say that again?
A vector Boston pre-multiplied by a matrix.
Well, I'll keep that in mind. I'll ask you in a second. So you say sort of this quadratic form. What's the computational complexity of that? Maybe let's discuss this first. I think this is a good point. So if you typically do this, right, by hand, you would first multiply a times x, which, as we just said, is an order n square operation. At that point, I will replace this here with a vector. So I then have row vector times column vector, which is this. So if I say roughly number of operations, I need n square multiplications to do the matrix times vector multiplication, and then I have n multiplications to do the dot product. So, and then plus additions and stuff, but we have something that scales with n square, and we have something that scales with n. And for large n, the stuff that scales with n doesn't matter. So this here is still order n square. Doesn't fit, but belongs here. Yeah?
Maybe if we have one more x, y, and z term.
Okay, we'll talk about this later on. I'll keep your example in mind.
Maybe a matrix product.
If I have a matrix times a matrix, and just for simplicity, I say that both of these are quadratic n by n matrices, then my result is a matrix. So to compute each element, I already have n square operations. I have to compute n square elements, and each element in a matrix multiplication is row times column, right? It's basically a dot product. So I have n square dot products. So I have n square times n operations. So this would be done in 3 for loops, right? So you go through outer for loop, go through the columns of your resulting matrix. Next for loop, go through the rows of your resulting matrix. So now I can visit each element of the resulting matrix. And then that element that I get is take that vector multiplied with that vector in the sense of a dot product, which requires another for loop. So I have 3 nested for loops, order n cube operations. And you can continue this, but we will not need anything larger than order n square in this lecture. Now comes an important note. If I have something where I say that is of order 2n, it's exactly the same as order n because, and this now goes to sort of this formal definition again, we have this constant c here, and that can be anything, right? So even if some operation has twice as many, or some algorithm or problem has twice as many calculations, we are only interested in the scaling. And this would be the same as order 100n. They are all the same. And I talked about this briefly in the last lecture, but if I look at 2 algorithms, right, and I say algorithm 1 has 1,000 times n operations. Whatever this algorithm does, right, the exact number of operations is 1,000 times n. Yeah, 1,000 times n floating point operations. And then I have another algorithm that is 10 times n square operations. This one is order n. This one is order n square. And it seems like they're almost the same, right? And then I could write another algorithm that is 10,000 n. Which of these is the best? If you just look at order, right, this is order n, this is order n, this is order n squared. And this would be order n squared. So if I just look at this, these 2 are equal, that one looks worse. If I look at the reality, these 2 are equal means 2 completely different things, right? But it could be, just to make this more fun, that I say this has 10,000 plus 1,000 n operation. So you see already, right, how I pick my n, one of these gets better than the other, right? If say n is 1, then this is actually better than this. but this is going to be the best, right? 10 operations, 10,000, 11,000 operations, 10,000 operations. If I go n equals 2, then all of a sudden this is the worst, right? This is better than this, but this is still going to be the best, right? Because we're doing, for n equals 2, we're doing 40 operations, right? So you can see for a large, n has to be very, very large that these here start to win. And that's something that's important to keep in mind, right? That this is not the whole story, right? This is a good tool to reason about very large n, but you have no idea how large n actually has to be for one algorithm to win over the other. This idea that the exact number of operations doesn't matter has an interesting application or implications, or an interesting implication for rigid body systems. Because so far we did this very generically. We said there's some problem size n. But for a rigid body system, what should we use, right? Do we use NB, number of bodies, or NQ, the number of joints? What is our problem size, right? What determines our problem size, NQ or NB? You say NQ. Who says NB? The correct answer is it doesn't matter, right? Because we have the number of bodies is smaller or equal than the number of degrees of freedom. This is sort of one corner case where each body is connected with a single 1 degree of freedom joined to the next body. So I start with ground, I add a joint, I have one moving body, I add a joint, I add a moving body, add a joint, I have add a moving body. So sort of on the lower end of things, the number of bodies cannot be larger than the number of degrees of freedom. On the upper end, the number of degrees of freedom cannot be smaller than 6 times the number of bodies. Right? This is sort of the extreme case where between two bodies I always inject a 6 degree of freedom virtual joint. So I have basically NB bodies floating freely around, which are all weirdly connected with these 6-dimensional virtual joints. But in reality, we just have NB floating bodies. Right? So there's a limit how large NQ can be in relation to NB. And since it's bounded between 1 and 6, it doesn't matter for us whether n is NQ or NB. Right? The problem size, when we talk about n, it can mean both, because these two quantities are limited. Right? They're related to each other's. So as a consequence, it doesn't matter. If n is NQ or n is NB. And then the other note that you should take from this is that the results only matter for large n. And then there's a question of what does large mean, right? Which this does not answer you, because you don't know, right? In order to know what large is large enough, you need to know the exact number of operations and not just their bounds. Okay, questions?
So the takeaway from this is we cannot judge the complexity based on the order.
It gives you a good guideline how algorithms scale, but it doesn't give you absolute numbers, right? And it doesn't tell you how large n has to be for one algorithm to be better than the other, right? And here what you basically see is that an order n square algorithm can be much better for small n, but if you set n to 1,000,000 here, this is going to be way worse than this, right? By a factor of 100. It's not, that's the point, right? It's not the whole story. And I will show you some examples today, and we can discuss what this means in terms of practice. I have a question for you guys. Now that you all understand computational complexity, my question is, what is the computational complexity of this? This is what you had in mind, right? This triple product. So this is why I didn't want to talk about it before, because I think this actually makes a good check. What's the computational complexity of this? Order n square, order n cube. What do you think? Give it a minute, and then we'll take a vote. Make up your mind. Okay, who thinks this is computational complexity order n, linear? Who of you thinks that is quadratic? All right, I have almost an even split. Who thinks that is O(n) to the 3, cubic? We have 2 cubic. Okay, you're almost all right. Why? Who said linear? What's your rationale?
You multiply it, first that it results in a scalar, and then the scalar with so first the dot product and then the scalar multiplication with the.
So Liam says, let's first do this, which is a dot product, which we know scales linear, and then I have a scalar, and then you multiply that scalar with a vector, which is again linear, which means each element has to be multiplied with a number, so one for loop. So you have a for loop for the dot product, and then not nested, but afterwards you do a second step, a second for loop, where you do the vector times scalar multiplication. So this is order n, an order n operation. You see where this is going, right? You're laughing. So if I do it this way, what is the computational complexity of that operation? N squared, right? So I first do this guy, column times row. So I do this one, which scales quadratically, and then I do matrix times vector, which is also quadratic. So I have 2 order n square operations, and the total complexity is order n square. This is the point where stuff that looks pretty isn't necessarily pretty, because we're kind of, right, when we write this as mathematical equation, we're not only tempted, but we have been taught to get rid of these parentheses, right? These are associative, so I can multiply them in any order I want, and so we leave the parentheses out, because it doesn't matter mathematically. But as soon as you put it in a computer, it does matter. And it matters massively. And I want to show you this. And to introduce this, I have to ask you, who of you knows who Pascal Jaufmann is? The study manager of engineering cybernetics. Because a few years, Pascal was in this course. And then when I presented this, he raised his hands and said, so what is MATLAB doing? Right? If you give MATLAB just this, what will MATLAB do? And then this is called Pascal's Questions Memorial Example, in memory of Pascal's question. So next time you talk to him, let him know he's famous. So we tried this. So I have here long vectors, n equals 5,000. And I compute things in different ways. The details, I think, don't really matter from the stuff below, but this is without parentheses. This is sort of the cheap version. This is the expensive version. and then I do transpose, and we were interested in what happens if you transpose everything, if their MATLAB, does it have a preference for row or column vectors. And if you ever want to know how fast your code is running, don't just hit run, but open this context menu here, and there's a function called run in time. There's actually a bunch of very useful functionalities. This pause on error, pause on warnings. Maybe you notice when MATLAB throws an error, you cannot look into the variables, and then you set a breakpoint and you go in there and you try to set the breakpoint right before the error. Here you can basically set an automatic breakpoint. Whenever something goes wrong, MATLAB will stop as if there was a breakpoint, and you can look at the variables and you can better research why your code failed. But here we're going to do run in time. And then while we do run in time, I shouldn't touch my computer just to not throw off the results, because if there's other operations happening in the background, MATLAB would slow down, and this would then bias the results. And then you get here the total computation time, almost 9 seconds that this took. Which is, of course, much slower when you do run in time, because it has to time in the background. So if I just run this, it's going to be much quicker. And I can click on this, and then it first tells me which lines take the most time. And if I scroll down, I basically see here a heat map of where the code spends time. So initializing the for loop doesn't take any time. Initializing these vectors, even though there are 5,000 elements, doesn't take any time. And then you immediately see that MATLAB is not smart. If you don't give it the parentheses, it starts front to back. So it will first evaluate this product, and then create the matrix, and then evaluate this product. And the difference is gigantic, right? So adding these two parentheses can speed up your code by a factor of almost 1,000. And that is here based on the scaling law. If you do it transposed, you of course have to set the parentheses differently. But here MATLAB would still go sort of stupidly left to right. And then for the transpose problem, of course, the parentheses have to go front. So here it would automatically, or by default, would use the better version. And you see a little bit how stuff scales. So I then repeat everything with a vector that has 10,000 elements. So the stuff that should scale linearly should take twice as long. And you actually see that these are now 2 milliseconds instead of 1. Plus measurement noise. And here it should scale by a factor of 4. So we get 6.8 or 6.5, 1.3, 2.6. Ballpark, it's there, but it doesn't scale exactly to 4 times, because there's still a lot of operations that are not quadratic in time. Or that scale slightly better, because you just do them once and you don't do them within the for loop. Just imagine, right, if I have 2 nested for loops, executing this inner for loop is something that I have to do n times, setting that up n times instead of n squared times. So the actual scaling is something like constant plus something times n plus something times n squared. Okay, questions? No? Meaning for us now, we should be very careful when we look at a problem like this, that to make sure we do this, right? And not do this. But who would be, yeah?
Have you tried it with other languages?
No. Could be interesting as well, right? But then again, who would be, now that you know this, who would be so stupid to do this instead of this if you have this in front of you, right? Good. Let's do an actual mechanics example. Now that we have established what this order n notation means, and the example that I want to do with you first is a very simple one. This is inverse dynamics, where we just rearrange our equations of motion in their canonical form to read tau equals m times q double dot minus f minus g. What's the computational complexity of evaluating inverse dynamics? Just evaluating this equation. Computational complexity, n squared. Yeah, the dominating thing here is mass matrix times q vector, and the mass matrix is an nq by nq matrix. So we have here computational complexity order n squared, right? And this is because my mass matrix times the generalized acceleration, right? This is a nq by nq matrix, and that is what dominates the computation. That, of course, is if you know M, right? If you know the mass matrix, but the first step that we do is we have to compute the mass matrix. What is the computational complexity of computing the mass matrix? And remember, right, when we use our projected Newton-Euler equations, we say the mass matrix is the sum over all bodies, where we have a Jacobian transposed, and this would be the translational Jacobi transposed times mass times Jacobi transposed. And then there's going to be a similar expression for rotational Jacobians, right, with inertia. Doesn't matter. What's the computational complexity of this? Computing the mass matrix. You say order n to the 4, and I think where you're coming from is you say I have matrix times matrix, which is order n cube, and then I have to sum over nb bodies, so we get order n to the 4. You have to be a little bit careful here because these Jacobians are not really n square matrices, right? So a Jacobi in this context has nq columns and 3 rows, which means it's actually more like a vector in terms of scaling, right? If I double nq, it will be twice as long, but it will still have 3 rows. So what I have here is more this idea of a column vector times a row vector. And that product then gives me a partial mass matrix, and each element of that partial mass matrix is basically 3 elements of the Jacobian times the corresponding 3 elements of the transposed Jacobian scaled with m summed up. So for each element of that partial mass matrix, we have 5 or 6 operations, but it's always going to be constant. That doesn't depend on NQ, right? I think that's, so I'm glad that you mentioned this, because this is something that is very common. I'm sure others thought that as well, right? Here you have to be careful that it's matrix times matrix, but the matrix does only scales in one direction. So we should think of this more as a vector. But that still means I have here a operation that is order n square, because I have to compute this partial mass matrix. And then I do this n times. So you get a total of n cube, or operations that scale with n cube. So in reality, the framework as we set it up right now if I want to do inverse dynamics, it scales cubically with problem size, right? And for robotics, maybe that doesn't matter because we're talking about robots that have 3, 7, I don't know, 42 degrees of freedom. But for other systems, this may become important. Can we do better? And this is just a guessing game. If yes, by how much? What do you think? Or maybe let's start with this. So what's the theoretical limit? How much better can we get? What's the lower bound? N. Because just writing tau as a vector is n operations. Just storing the result is going to be n operations. So we are not going to find something that's constant, but sort of the theoretical lower bound is n. So what's the best we can do? What do you think? Should we take a vote? Who thinks this is the best we can do? N to the 3. I'm way too suggestive in this class. No one's going to dare to raise their hands. May I show you proof that this is, you cannot do better than n to the 3? Who thinks we can get it down to n square? And saying computing the mass matrix, writing down the mass matrix is n square operations. That seems like a reasonable lower bound. Now I'm inserting doubt into these people, right? Can we do even better? Can we do it without writing a mass matrix and do it in linear time, order n? Who would believe that that's possible? You don't believe me. Dynamic programming. I don't think that will help with the scaling. But the fun bit here is, and I think this is really interesting, is you can do this in order n. Right? And of course, we already means we cannot do a mass matrix. Right? Because just writing down mass matrix would be order n square. But we can do it in order n. And it basically requires throwing everything out that we learned in this course and starting from scratch. And then we get an algorithm that is called the recursive Newton-Euler algorithm. And the recursive Newton-Euler algorithm is, I'm going to make a quick sketch first. Considers each body individually. And we have a body that has a center of mass. And because we're doing inverse dynamics, we know accelerations, we know positions, velocities, we can all compute this. So I know what my D'Alembert forces are, right? It's minus the linear momentum of this body minus pi, and I get a D'Alembert torque, which is going to be minus, sorry, there's a dot missing, of course, the change of linear momentum, and then consequently my D'Alembert torque is going to be minus the change of angular momentum. Because I know my positions, I can go ahead and compute gravitational forces, know exactly in which direction they are acting. And this would be here body I. And then, of course, body I is connected to some other body. Body I minus 1 to the left, body I plus 1 to the right. And that connection happens through joints. And these joints, they have active degrees of freedom, which are driven by some joint torque tau, which I will call tau I here, and tau I plus 1 here. Right. If we have branches in there, my numbering scheme would have to be adapted a bit. This numbering scheme only works for kinematic chains, but you can imagine how to extend this if a body has multiple child joints. So each joint has an active component, tau I, and this is the thing that we want to compute. And then it will also have some passive components. So there's going to be some constraint force, FCI, which of course acts here on the opposite side with a minus FCI. And there's going to be corresponding constraint torques, MCI and MCI with a minus sign. And in total, the total number of components that we have here is 6. Right? So if I have a rotational joint, then I have 3 forces, 3 constrained forces, 2 constrained torques, and 1 active motor torque. If I have a prismatic joint, I will have 3 of these MCs, 3 constrained torques. I will have 2 of the constrained forces, and then 1 active motor force, right? And then if you, let's say for whatever reason, you're interested in ball and socket joints, I don't know if that ever happens, right? You would have 3 active torques here corresponding to the 3 degrees of freedom of your ball and socket joint, and 3 blue components. But the sum of these blue plus orange is always going to be 6 elements. And then, of course, this happens here as well. So I have here my FCI plus 1, which now at my current body comes in with a minus sign. And I, of course, also have joint torques. Right? And the exact nature depends on the type of joint, depends on number of motion primitives in the joint, and so on. That's just the free body diagram. Now, what do we know? We know accelerations, so we can compute P dot and L dot. We know configurations, so we can compute this. What we don't know are the constrained torques, constrained forces on both the incoming and outgoing joints. And of course, we don't know the tau i's, right? This is actually what we want to compute. So we have how many unknowns? 6 on the left, 6 on the right, 12 unknowns. How many equations? Well, for this rigid body, we can set up the equations of motion for a rigid body, so the Newton-Euler equations of rigid body motion, which is 3 equations for linear motion, 3 equations for rotation, 6 equations. 12 unknowns, 6 equations, there's nothing we can do. Who has an idea to fix this?
Can you calculate from the leaf to the ground?
Exactly. If I keep going, I will eventually come to my leaf, or a leaf, right? If it's just a chain, I'm in a leaf. And the important property of a leaf is that I don't have that, right? I still have these constraint forces. So they're still at FC, let's call it N, just to give it a name, and an MC N, and there's a tau N. And then there's, of course, the reaction forces on the next joint. And I have my D'Alembert forces and my active forces. So all of this still exists. Sorry, this is just a sketch, so you don't even need to copy all the details because this is more about the principle, right? But if I do this free body diagram for a leaf, which by definition, because we're only talking about kinematic trees here, right? This will not work for loops, but if I limit myself to kinematic trees, for this leaf, I can set up 6 equations for 6 unknowns. And I can figure out what these constraint forces and what this torque tau n is. And then the whole thing collapses, because then for the next body, towards the root, moving towards the root, I know what these forces on the right-hand side are. I only have my unknowns on the left-hand side, and I can keep moving towards the root, always knowing the quantity on the right, solving 6 equations for the 6 unknown quantities on the left, and I can move all the way to root, extracting the tau i's along the way. That was a rough sketch. Let's try to formalize this a little bit more and actually write down the equations of motion. And to this end, I will zoom in a little bit. I have forces that are acting at the center of gravity by definition or by choice. For these active forces, we often assume gravity acts at the center of mass. If I have something, an external force that acts off-center, I could replace it by an equivalent force at the center of mass plus some free moment. The D'Alembert forces, so minus pi dot, acts definitely at the center of gravity, and my D'Alembert torque is a free torque, which is expressed about the center of gravity as well. Then I have my joint connecting towards the root, which is here given by a vector, and that vector has a name. That is the vector r as ds. Right, because this is the successor body of that joint. So this is the vector r as ds, the joint location. And then I have here a 6-dimensional quantity that I will now call fji. So I don't call it constrain. I call it j for joint. And I call this moment mji. And the notion here is that this includes tau. So what I'm saying here is that the active forces, the taus and the constraints, as we saw before, right? Whatever we do, they're going to give us a 6-dimensional force quantity that we just call the force across the joint, and I call this as Fj, or torque across the joint, Mj. And this is towards the root, and then towards our leaves, we have a vector r p dp, because for child joints, this body would be the predecessor body. Did I screw it up? No. You just had... Oh, sorry. You want one? Already has your tape on it. Now you know how I feel. Does it work? Okay, can I have this back afterwards? Here we go. So this would be RPDP, right? From the predecessor to the child joint. And here, sort of same story. We have now minus Fji plus 1. So here we talk about the reaction forces. And we have minus mji plus 1. And you can imagine, right, there's multiple successors, so there could be more of these torques and moments, and we would have to adapt our numbering scheme somehow. But let's just sketch that out. Now, sum of all forces equals 0, or the way I will write it is Fji is equal to everything else with a minus sign. So we get plus the D'Alembert force minus the active force plus, and I will write this with some sloppy notation as the sum of all j I plus 1. Right? If there's more than one, we'll just sum up with some numbering scheme that I'm too lazy to figure out. And then we can do the same for torques. So we have our free torques. So this would be the D'Alembert torque. The change in angular momentum plus, and now we have to do a little bit of math because the constraints that are acting here are also generating torques. And so I have here the vector minus rs ds cross product. So my reference point for the torques that I'm writing down is here, this moment, right? This point, this joint. So cross product with, and now we have pi, also with a negative sign, pi dot minus fa active forces. So these are the torques generated by these forces around my joint here. Then we have the sum of all free moments at our child joints. So they don't need any lever arm. And then we have to add another torque coming from the joint forces. So this would be, now the total vector would be rpdp minus rsds as the lever arm of these forces. And there we get a cross product with the fj I plus 1s. And again, right, there is a summation symbol in here which only goes into effect when we have a when we have more than one child joint here and here. And with that, we can now put together the algorithm. And our algorithm is going to be two parts. The first is that we start with root. And recursively compute all, body orientations. So A inertial reference frame to body I reference frame, all positions, so vector ROI, center of mass velocities, angular velocities, center of mass accelerations, angular accelerations. The reason why we need this is because we need these lever arms RPDP, RSDS, right? To get that, we need the body orientations. We need the accelerations so we can compute the change in angular and linear momentum. And then depending on your system, you may also need the geometry to compute your FAs. Right, so I have to first do kinematics. What's the computational complexity of doing kinematics with our outward pass? And to answer that question, it's best to remember how we played that algorithm in class. Right? The outward pass algorithm was update everything, and I started with root, and root turned around and told its child joints, hey, update, hey, update. Then the joints did something. They had to do some computation and then told their successor bodies update, update, which also told their child joints update, update, and the child joints did again something. But every joint and every body was basically called upon once. And every joint and every body did the same thing, which was independent of the number of bodies, right? The way we store stuff in this decentralized structure, the bodies don't even know how many other bodies are there, and the joints have no idea how many other joints are there, right? A joint computed, took a position, velocity information, which is 6-dimensional, 3 translation, 3 rotations, did something with the 6-dimensional thing and passed it on. Right? And the body, all they did was they remembered that 6-dimensional thing. And then you do this many more times because you have velocities and Jacobians and accelerations. Right? So you have to do this a few times as a joint. So the total number of calculation is a lot, but it's constant. It doesn't depend on how many other bodies are in the system. And that's the important thing. Right? This one step in my recursion has constant cost. Every body does the same thing. Every joint does the same thing. So the overall complexity scales with order n. And then we are prepared for doing an inward pass, going in the opposite direction. So this would now be the second step of the algorithm, where we start with the leaf or leaves. And recursively compute all Fji and Mji. So we start with a leaf where these here are 0. And just solve these equations to get Fji, Fji, and then we move to the next body. These are then given, and we can solve for Fji minus 1, Mji minus 1. And if you look at these equations, right, they're complex, but again, they don't scale. This is all 3-dimensional. This here is all 3-dimensional. So there's many operations, but none of this scales with the number of degrees of freedom, right? It's constant. Every body has to solve this one equation once. And then we move on to the next body and solve that equation again. So we will solve these equations, we will just insert numbers, n body times. So this here also takes order n amount of time. And along the way, right, as we compute Fji and Mji, we can now extract tau I from these joint quantities. That's the step where I'm skipping the math here, but you can imagine that this is a projection that involves our joint Jacobian. I have these 6-dimensional quantities, and I project them with the joint Jacobian down into the motion primitive of this joint. I'm basically just extracting the active components of these 3-dimensional components. And that I do once I have computed an Fj, right? So I have to do this once per joint. And I have to do this to basically go from 2 3-dimensional quantities to something lower dimensional, right? Whatever the number of motion primitives it is. But again, it's not something that scales with NQ. We just have to do it once per joint, which means the overall complexity scales with order n. So we can do inverse dynamics in linear time with this algorithm. Is it pretty? No. Right? It's pretty brute force, and compared to this, oh, come on, look at this equation. Isn't it beautiful? I mean, every mechanics professor dreams of equations like this, right? Compact, matrix notation, few symbols, every symbol has a distinct meaning. And then, I mean, compare this to that crap, which tends to be much, much more efficient. I have to think about it. Do you want to talk about first why is it more efficient, or should we do an example? We'll do an example first. I'll skip stuff. Sorry about this. I'll skip about why it is efficient, because that's a longer discussion and I won't be able to finish today. Give you something to discuss over lunch. Where does this come from, right? Order n to the 3 and order n. So where did we basically screw up when we generated this beautiful equation? What I wanted to show you instead is how we can use this to do other things more efficiently. Because we saw before that computing the mass matrix is an order n square, n to the 3 operation. Yeah, pretty slow. Can we do better? And we already say here, right, we can do m in order n square. We cannot do better than n square, because just writing down a mass matrix is an order n square operation. But I will call the algorithm that we just wrote, our recursive Newton-Euler algorithm, as a function, an inverse dynamics function, which takes 3 inputs: the current positions, velocity, and accelerations. And that function returns the required torques to create that motion. And what that function does is equivalent to evaluating our equations of motion in their canonical form as mq double dot minus f of q and q dot minus g of q. And despite what we write on the right-hand side, right, which if we would actually perform this calculation would be an order n square, or to compute the mass matrix order n to the 3 operation, we can compute this torque tau in linear time. And that's super useful as it is, because it allows me, for example, to evaluate this function inverse dynamics with this guy here. Right? So if I set q dot and q double dot to 0, what is this function ID giving me? Sorry? Didn't hear that. What do you think? What do we get there? No, it's different, right? It's similar idea, right? Where we computed accelerations and then set q double dot to 0. Here's a similar idea. I compute joint torques tau, and then set q dot and q double dot to 0. So, right. So we get, if I set q dot and q double dot to 0, I can look at this, and I know that this will remove this guy here. This will be 0. And what I get when I evaluate IDQ 0, 0, I get minus g of q. So in a controller where you do gravity compensation, right, using this recursive Newton-Euler algorithm can be quite useful. But then when you have it, of course, you should do some feed forward in terms of positions and in terms of velocities and accelerations. But we can, again, right, we can misuse this. I show you another way of misusing this. So now I do ID of Q 0, and then I do a weird vector, which is a 1 in the first element and a bunch of zeros in the rest. And I subtract from that my gravity compensation. What is that going to be? So let's see, right? The first call will give me m times q double dot, where q double dot is this, minus f. F is 0 because the velocities are 0, so minus 0, minus g. And then I subtract from that minus, and then I have mass matrix times accelerations are 0, minus f is 0, minus gravity. And we see that the gravity terms cancel each other. This is 0, and we are left with the mass matrix times 1, 0, 0, 0, which will give me
which torques we need to accelerate in the first Q.
Yeah, or if I just look at this, right, mass matrix times this vector is just the first column, yeah, first column of my mass matrix. So I can compute a column of the mass matrix in linear time, right? I called only this function ID, which scales order n. I have to call it twice, so yeah, it's order n times 2, but that's the same as order n, doesn't matter. And that gives me a column of a mass matrix. And then, of course, you see where this is going. I do this n times for each row. So by cycling through q double dot, we can get the mass matrix in n, actually, I should say 2n calls to this function ID. The exact number doesn't matter, but I just realized that this one will give you the same result. So you have to just call this once, and then you do this n times, so you have n plus 1 calls to ID. But none of this matters because we're just interested in the scaling, and the scaling is n calls to an order n algorithm. So we can compute m in order n square. And I want to show you that in an example. And this is example 14, called Performance Comparison Numerical. And here I implement these two ways of computing a mass matrix. I first define my number of degrees of freedom. And you see that I already have a very high expectation of what large will mean in this context. I will evaluate or compute my mass matrix once. And I'll do this for our standard example of an n-link robot or n-link pendulum. Right, so there's 50 to 2,000 of these links. Length is 1, center of mass is always smack in the middle, mass is 1, inertia is 1, just some random parameters. And then I will evaluate, pick a random vector for these our numerical values, and then evaluate the mass matrix n trials, but here n trial is just 1. So I'm evaluating one mass matrix, computing one mass matrix for a very large system. And there's the numerical order 3 algorithm, and there's the numerical order 2 algorithm. And the reason why I put them into embedded functions is so I can better compare the execution time of these algorithms. Let's start with the numerical order 3 one, where I extract my parameters. And then basically there's just a bit of initialization. But what I want to do is I want to compute my mass matrix. So I go through my NQ bodies. I initialize the mass matrix with sort of this term J transposed MJ plus blah, blah, blah for the first body. And then in each iteration, I add an additional body to it. To do this, I have to sort of recursively update my Jacobians, skipping all the details here. But the important bit is basically I have one for loop here. And then within this for loop, I do these multiplications that give me partial mass matrices. Right? So JR_num is a 3 by NQ matrix. And I basically have this column matrix times, column vector times row vector calculation that we see here, right? To compute my partial mass matrix for rotation and translation. And so we don't see the 3 nested for loops, but to do this here, MATLAB internally has to do 2 nested for loops because it's computing a partial mass matrix which has n square entries. So this is n square operations, and then we do this for each body, so n to the 3. This is the order 3 method. Here we have the numerical order 2 method, which is a little bit harder to explain. And I start here in the middle, where we see a outward pass as a for loop. So I go for j, which is actually should be I to correspond to the lecture notes. We go from 2 to NQ. We do an outward pass. And you see that I can compute positions, as orientations, positions, angular accelerations, linear accelerations in some recursive form, right? I always look at what's the orientation of the previous body, what's the position of the previous body, plus what's the orientation. And then there's somewhere there should be a joint in between. Here's the joint, right? But you can, without again going into the details, I think you believe that this is the outward pass where we do kinematics. All of these calculations don't scale with the number of degrees of freedom, right? They're all, in this case, mostly scalar or 2-dimensional calculations. But I have to do this NQ times, right? Moving outwards, joint by joint by joint, moving outwards. Then I initialize the inward pass, where this is my sort of my constrained forces and torques on the right side, which I set to 0 because I start at the leaf where they're 0. And then I do an inward pass. So I go from NQ and -1 steps back to root, moving backwards. And I compute or evaluate the Newton-Euler equations for this body. So what you see here is verbatim the equations that we just wrote down, where the sign terms here correspond to these lever arms, RP, DP, and RS, DS. And so I can compute these blue quantities, and then here I extract my joint torque. We're extracting the joint torque in a planar system, if you have a rotational joint, is just the same as saying that's the torque. Right? The motor torque is the torque across the joint. And then I have my tau. And so here, everything here is linear. Right? This is the Newton-Euler, recursive Newton-Euler algorithm. And then wrapped around it, I have this idea where I compute the mass matrix column by column, where I essentially define here a 0 of my Q double dot, and then I set the element I to 1. So this is where I generate this vector 0, 0, 1, 0, 0, 0, or wherever we are, which gets multiplied, in a sense, with the mass matrix. And with that vector, I then initialize my recursive Newton-Euler algorithm. And at the very end, I'll just take that torque and add it into the mass matrix. This assumes no gravity. I don't know, it probably says somewhere in the small print that we don't have gravity, so I don't have to do the minus g compensation. Right? I just say this is my rho. Questions? Let's run it. Run in time. And the question, of course, that I want to enter is which algorithm is better. And we start with an n of q of 50. And maybe I'll make a little list here. So this would be n. And this would be order n square, order n cube. And then we can note execution times. So we have order n square, execution time 0.03. And the other one was order 3.007. Winner. So the worst algorithm is 5 times faster than the bad algorithm. Sorry, the worst algorithm is 5 times faster than the better, theoretically better algorithm. Why is that? There's 2 answers to this. Answer 1 is because we didn't pick n large enough. And then answer 2 is because there's something inherently better in sort of this than that. And that has to do a lot with MATLAB. Right? The fact that MATLAB is a scripting language, so everything that I write here is evaluated line by line and has a lot of overhead. So if I have a for loop, just running that for loop generates a lot of overhead. And here I have 2 nested for loops. Here I have 3 nested for loops, but only one of them is sort of script language. And the other, the 2 in the middle, are done through these matrix multiplications, which are implemented very well in MATLAB. So sort of this algorithm is implemented by me in a scripting language, slow. This algorithm, the core part, is implemented in, I think, Java with a very, very efficient algorithm, very efficient memory management, pre-allocation, everything. This makes, of course, this part comparably much faster. Yeah? But we have to see how stuff scales. And now I go up by a factor of 10. So we expect that this takes 100 times as long, and this takes 1,000 times as long. Order 2 takes 0.73 seconds. And order n cube, what did we get there? 0.66. still the winner. And we don't see the scaling that we expect. Right? I said this should scale by a factor of 1,000, so this was 500. So we scaled problem size by 10. This should scale by 100. Doesn't. This should scale by 1,000. Doesn't. And that has to do, again, with the fact that not everything scales with n to the 3, right? Some things scale just with n to the 2 or are constant. Just starting the program, starting the profiler, for example, is in constant time. Let's double again and see if that's enough, if 1,000 is large enough for problem size. And you see sort of the issue with this. So here, factor 4, factor 8 in time. And we get execution times, order n square, 4.4. And order 3, 5.5. So for this problem, right, problem size where the better algorithm wins is 1,000. And I can run it one last time. To see if we actually get to the scaling laws. But here we're already close, right? This times 4 is roughly what we would expect, right? Scaling of 4. Here we would expect the scaling of 8, so 1.2, 2.4. We almost see that scaling of 8. And then you can imagine, right? If I do 5 seconds times 8, that's 40 seconds. So I should expect that I have to continue talking for a bit longer before this actually converges to a solution. Awkward. Anyone wants to tell a joke?
Why do programmers use dark mode? Because light attracts bugs.
That actually took a moment. Thank you. There we go. I wanted to say we need another joke. But here you see, right? 45 seconds. So we get the scaling. And you see how sort of internally, right, a for loop is way, way slower than doing a large matrix multiplication. But that advantage that we initially had for small n at some point goes away, right? Even these matrix multiplications that are implemented highly efficiently in MATLAB, at some point they suffer from these scaling laws. And now here I get the point where sort of this factor 8 takes over. Here it should be a factor of 4. So this one seemed a little bit high compared to here, and now we don't get a full factor of 4. So some of this also changes from execution to execution. If I run this again, I get different numbers, right? If I move my mouse or if in the background I get an email, this will slow things down. You have a question?
What's the difference between total and self-time?
It tells you a little bit. So if I can scroll down here, can I? No, I cannot scroll down here. But it basically tells you that numerical order 2 calls this function cross product. Actually quite a number of times, as you see, which is evaluating, this guy here, and is my well-coded version of a cross product in 2D. And so the function calls another function, and then basically to separate where the time is really spent. And if I would click on this to look at the lines, you see here, these are sort of the big chunks, and then I would have to basically go into this function, where I would see that in here I have my cross product somewhere in there, and And then I can dig even further and say, okay, when calling cross product, where's that time spent in this function cross product, which is surprisingly spent in the function end, right? Which tells you this is a scripting language where MATLAB's like, oh, I have to, I don't know, finish the execution of this function. I want to show you this as an example to show you that this eventually gets you. But this robot with 2,000 degrees of freedom, I don't want to build it. Yeah, and if you don't have it, right, if you just have 500 degrees of freedom, then it's not worth using the recursive Newton-Euler algorithm. Or, you know, if you move to a different programming language where everything is compiled and efficient, this can look very different, right? Even for smaller numbers, this guy could potentially win. Still have this question, right, that you need to discuss over lunch, how it can be that one version is order n to the 3 and the other version is linear. But we'll discuss this on Thursday. Have a good week until then. See you.